So till now we have discussed about the Fourier series, Fourier transform, which we are working in the continuous time domain. Then we discussed about the discrete Fourier series, discrete time Fourier transform. Then we also discussed about the DFT. Now these three transforms, they were working in the discrete time domain. Okay. Now again we are coming back to the Laplace domain or Laplace transform, where this transform it is being used for the analysis of the continuous time signals and systems. Okay, and this system, what it does is that it is the most generalized transform of the Fourier transform. So a Laplace transform is nothing but a generalized transform of the Fourier transform. So the problem with the Fourier transform was that we were able to analyze this what do you call energy signals and power signals, but we were not able to analyze signals which were growing out of bound. Okay, so for the analysis of that kind of signals and systems, we needed a transform or a transform which would help us in analyzing those systems where the output was going out of bound or the signals that are going out of bound. Okay, so then from this Laplace transform, as I told you, that it is basically for the continuous time signals and systems. Then while we go towards the digital system, we need the Z transform. Okay, and this Z transform it helps us in uh, analyzing the discrete time signals and systems, including the digital signals and systems. Okay, so this is the story. But before we can go for the Z transform, it is customary to understand what happens in the Laplace transform. Okay, so we will start with the Laplace transform and slowly we will be moving towards the Z transform. Okay, so the problem with the Fourier transform was that if you see over here, this is our Fourier transform equation. So what was happening is that Fourier transform of x of t, which is equal to j of omega, it is nothing but integral of minus infinity to infinity x of t multiplied by e to the power minus j omega t. Okay. Now, if this xt it is going out of bounds, then what happens is that we will not be able to analyze those signals. Okay, and if you consider the output of a system, if the output of the system is growing out of bound, then we will not be able to analyze the system itself. Okay, so for that reason, so what we do is that we multiply xt with an exponential function e to the power minus sigma t, where sigma is a real value. Okay, so if we give a minus sign, then what happens? It becomes an exponential signal. And what type of exponential signal? Decaying exponential signal. Okay, so the xt it would become the decaying exponential signal. What does this mean? It means if you look into the decaying exponential signal, if you see this as the time t and amplitude a, so a decaying exponential signal it would look something like this. And at time tending to infinity, our amplitude it will tend to 0. So that means if you multiply something, say xt, even if it is going out of bound means it is ever increasing. Okay. Now if it is getting into the ever increasing domain, so what will happen? So that amplitude at time tending to infinity multiplied by 0, it would become finite in number, or it will tend to 0. The amplitude would tend to 0. Okay. So because of that reason, what will happen? The system will become bounded signal and we will be able to analyze the signal. So this is what it has been done. So if you see and look into this equation, so instead of x of t, we are now taking xt into e to the power minus sigma t. So we get this equation, and just by rearranging, we get x of t multiplied by e to the power minus sigma plus j omega t. Okay. So now this function, it becomes the Laplace transform equation. Okay. And it is represented with x of s equals to minus infinity to infinity x of t into e to the power minus st dt. Okay. So what is happening? So basically it means s is equal to sigma plus j omega. So we are coming to a new complex domain. Okay. So if you see, this is the Laplace transform equation, and this is the inverse Laplace transform equation. So together they form the Laplace transform pair. Okay. Now we talked about the convolution integral, and over there we were talking about the Fourier transform, discrete Fourier transform we talked about. Now that happens also in with the continuous time signals if you consider. So we are having for the Fourier transform also. Now over here also for the Laplace transform we have this convolution integral. Okay. And for the digital signals we have to go into the Z transform. Okay. So over here we are having x of t, which is the input, h of t, which is the system impulse response, and yt we get xt convolution of h of t. And similarly, what we did in our discrete Fourier transform, if we perform the Laplace transform, we will get to the x's. Then similarly, we will be performing the Laplace transform for the ht, and we will get h of s. And by pointwise multiplication, we will be getting y of s equals to xs multiplied by h of s. And then if we perform the inverse Laplace transform, we will be getting to the yt. Okay. So what is Laplace transform and why it is needed? So Laplace transform, it is a mathematical tool that converts a function of a real variable into a function of complex variables. Okay. So over here, as I told you, we are having two parts because we are talking about the imaginary plane. So we are having two parts. One is the real part sigma and the other one is imaginary part, and the imaginary axis is our j omega axis. So this real part, it is regarded as, this sigma is regarded as a damping factor, and j omega axis, it is associated with the frequency. Okay. So we'll be having a plane where our y-axis is j omega and our x-axis is sigma. Okay. Now, why it is crucial, as I told you, because the Fourier transform, it only exists on the j omega axis. Okay. Fourier transform means we discussed that it is basically j omega. So where in this Laplace plane or the S plane, where we get the j omega, j omega is present at sigma equals to 0. So when sigma is equals to 0, our Laplace plane, it becomes the Fourier transform, or Laplace operator, it becomes the Fourier transform, and hence it is called as the generalized Laplace transform is regarded as the generalized Fourier transform. Okay. Now, what was the need? The need was that because, as I told you, it was not able to handle a large and important class of signals and unstable systems which were going out of bound. Okay. So how Laplace transform and Fourier transform are related? I just told you, when sigma is equal to 0, then our Laplace transform, it converts into the Fourier transform, and this is what it has been written. This is just for your answer for the examination purpose. So, what are poles and zeros in the context of Laplace transform? Okay, here we also have z transform transfer functions also, but for this moment we will be taking the case of the continuous time signals, and later on we will be discussing about this digital systems. Okay, so what are these poles and zeros? We already talked that when we talk about any system, specifically the LTI system, we have an input, we have an impulse response of the system, and we get an output YT. Okay, so the gain of this one, it is given by YT by XT. Now, if we convert this into the frequency domain, so what we will be getting? We will be getting Hs equals to Y of S divided by X of. And what are these? Y of S and X of S? These are all polynomials. So the roots of Y of S, that means since these are polynomials, they will be having some roots. So how we can represent the polynomials? Polynomials can be represented in this form: S minus A multiplied by S minus B multiplied by S minus C, and so on. So if we equate Ys equal to 0, and what we'll be getting? We'll be getting some equation like this, that is equal to 0. So at S equal to C, what will happen? This equation, it will become 0. Okay, so what happens then? When at S equals to C, what will happen to this transfer function? Polynomial, it becomes 0. So this transfer function, it becomes 0. So S at S equals to B, again this polynomial, it will become 0. So the roots of Y of S will be considered as the zeros of the system, and they are represented by this form, by a small o. Okay, so zeros, they are represented graphically as small o's. On the other hand, if you try to find out the roots of x of s, what will happen? When x of s becomes 0, h of s becomes infinity. Infinity means its amplitude increases multitude. Okay, its amplitude increases multitude. So what happens? Have you heard of this uh, phenomena when you are having these DJs and all these things? So sometimes you get a squealing sound. Squealing sound means there is a sharp sound. So what is happening? Slowly your system gets what do you call uh, amplified, and sometimes it gets very much the signal becomes too much amplified, and you get a squealing sound. Now when that happens when our poles, they are present on a particular frequency. Okay, that means we discussed about our this Laplace transform. What is the frequency axis? J of omega sigma omega frequency is present in the y-axis. So if we place a pole on a particular frequency, so what will happen? At that particular frequency, it will take the amplitude value to infinity. Okay, and when it becomes infinity, that means our system becomes unstable at that particular frequency, and that squealing effect is due to this phenomena because at a particular point the pole has been placed. Okay. Now the thing is that so the roots of x of s, what it is doing, it is pushing the h of s to infinity. That means the gain of the system, it is increasing. Okay. And hence these poles, they are represented with x. Okay. Zeros are represented with small o, and poles, they are represented with x. Okay. So the squealing effect, it is basically because of the resonance at certain frequencies. So while designing stable filters, we need to understand that the poles are always placed in the left hand side of the Laplace transform plane. Okay. So Laplace transform, it is given by this one. Okay. Relationship between the poles and system stability. A system is considered to be stable if its output is bounded by any bounded input. In mathematical terms, the system impulse response must tend to 0 as time t tends to infinity for the system to be stable. Okay. The behavior ht is closely related to the position of the poles of h of s in the complex plane. So if we place the poles on the left hand side of the S plane, so what happens? Our sigma is less than 0. That means we will be having sigma as negative values. So what will it will do? If we give any input x of t, what it will do to the x of t? Even if it is going out of bound, it will make this x of t bounded due to the multiplier of this e to the power sigma t, and sigma is negative in the left hand side pole. So it is bringing the input signal into a bounded form. Okay. And hence we have to place the poles on the left hand side. What happens if we place the pole on the right hand side? The sigma value, it becomes positive, and since it becomes positive, what will happen? It The output will grow out of bound. Okay. So the output will grow out of bound, and hence that is not desirable. Okay. What happens if we place the pole on the j omega axis? At particular frequencies where you are placing the pole, there will be a resonant effect. Okay. From where that resonant effect is coming? Our s is basically, we are in Laplace domain, we are having e to the power sigma plus j omega t. Sigma is 0, so it becomes e to the power j omega t. Okay. What is this given by? Cos omega t plus j sin omega t. So it is associated with a frequency component. So that omega t component, that is the resonant frequency. So if we place a pole at omega, then what will happen? Those sinusoid cos, represented with the cos omega t plus j sin omega t, they will be multiplying and they will undergo in the resonant form, and it will, at those specific point, it will take the amplitude to infinity. But at other frequencies, it will not have any problem. So hence this kind of system where the pole is being placed on the j omega axis, they are regarded as marginally stable systems. Okay. And in the case of marginally stable system, the systems neither grow out of bound, neither they tend to 0. Okay. So they will be giving you a resonant frequency, means you will be having some sinusoidal signals all throughout. Okay. So the placement of the poles, practical implications. So in practical filter design, ensuring that all the poles are placed in LHS of the ends of plane is crucial for achieving a stable filter. Okay. So while designing stable filters, the zeros can be placed anywhere in the Laplace transform, because placing of the poles, what it does not goes the output signal to infinity. In fact, it brings the system response to 0. And if it is on the frequency axis, at that particular frequency, the system response would be 0. Okay, the system response would be 0. In the case of pole, there was an increase in the amplitude at that particular frequency, but in the case of this zeros, it will be 0. That means it will remain bounded. So we can place zeros anywhere on the Laplace plane. Okay, but we cannot place poles on the imaginary axis or on the right hand side plane of the S plane. Okay, this you should keep it in mind. Then there is another term which is called region of convergence. Okay, so what is this region of convergence? ROC for the Laplace transform is the set of complex values s equal to sigma plus j omega for which the Laplace transform integral converges absolutely. That is, the integral of modulus of x of t e to the power minus st dt is finite. Okay. This region is always a vertical half plane of the form real s greater than a. Real s greater than a. Okay. So what does this mean? Where a is a real constant known as the abscissa of the absolute convergence. Okay. So what happens is that when we talk about any biomedical signal, they are regarded as the causal signals. Causal signals are right-handed signals. We discussed in our signals and systems, right? They are the right-handed signals. That means they start at 0 and they will go up to infinity. Okay, in that case, what will happen? Suppose we are having a pole at the real axis. Okay, so what it says, where should be the this region of convergence? Suppose this value, this sigma is equal to a over here. So it will be a vertical plane for real is greater than a. But for showing diagrammatically, what we usually do is that we pass it through the a, because if it has to be infinitely slightly away from the pole. Okay, so that's why for practical for the theoretical consideration or for depicting it, we show it that the region of convergence, this vertical line, it passes through the pole. Okay, but ideally it should not be. It should be, the condition is that real of s should be greater than a, and where it should be is always a vertical plane of the form real s greater than a. Where is real s greater than a? On the right hand side, right, on the right hand side. Okay, so the region of convergence of a pole for a stable system, it is on the right hand for the causal stable system. Now this is for the causality thing. Now why I am telling it is stable? It is stable because the region of convergence, that means, what is the definition? The definition is the integral converges absolutely. That means the dt, that is the integral of this factor dt is finite. That means at sigma equals to 0, our solution remains finite. And if it remains finite at sigma equals to 0 at the frequency axis, that means your system will be stable. So this is the stability criteria. Okay, so from the causal signal, if we are having a causal signal from across from the pole position, our region of convergence will be on the right hand side. And if the region of convergence it includes the j omega axis, that means the integral will be finite within that region, and since it will be finite within that region, our system is stable. Now if we place this pole on the positive side, again if you see over here, our region of convergence will be on the right hand side, but our j omega axis is not included. Since our j omega axis is not included, the system is not stable. Okay, got my point? Now if we give, if our signal is anti-causal in nature, then what happens? The region of convergence will be on the left hand side. Okay, will be on the left hand side. Now if we have a plane, if we have two poles like this, say pole A, say A1, A2. Okay, so usually the region of convergence should be like this. Okay, the region of convergence should be the overlapping plane like this. Yeah. It violates the stability criteria. Yeah. It may also be, it may also be, so in most of the cases, it should be within A and A1 and A2. Okay. So, did I mention this? Yeah? No. The bilateral Laplace transform. The ROC can be vertical strip between A and B. So A and B, if you get, so vertical strip between that. Okay. So that is for the bilateral Laplace transform. But when we are talking about the causal system, because our biomedical signals, they are causal in nature, so we'll be having this thing in more than A, greater than A. And suppose, yeah, this was for the bilateral Laplace transform. Okay. Now, say for example, it may so happen for the causal systems signals, we may have two poles again like this, say A and B. Now, what should be the region of convergence? Region of convergence should be whatever the pole which is on the right hand side. So we have to consider that, and then from there on the right hand side for the causal signals and systems. Okay. For the bilateral one, it should be in between A and B. Okay. For the causal systems, the signals and systems, it should be whatever is the pole on our right hand most side. From there, the right hand side plane, vertical plane, will be our region of convergence. So understanding of this one is important. Okay. Now coming to the Z transform. So this is the equation for the Z transform equation. This thing. So if you see, yn equals to h of z into z to the power n. Okay. Now if you see h of z, it should be equals to y of n multiplied by z to the power minus n, because it should go over there. Okay. So by looking into this, what is our h of z? H of z, we talked about that it is a polynomial. So basically our h of z is equal to, because n is varying, it is not constant, so it is summation of n equals to minus infinity to infinity h of n z to the power minus n. Okay. Y of n, it is the output, but basically for impulse response, what is hz? Basically the impulse response in the z domain. So it is h of n multiplied by z to the power minus n. Okay. So this is regarded as the bilateral z transform. But what does it say? What does this indicates? This indicates that suppose you are given with h of n, which is the impulse response of a system, say -1, -2, sorry, it can happen -1, -2 also, but I am taking the positive numbers 1, 2, 0, 1. Say for example, so at the initial stage, let us take when h of n starts with 0, because that is true for the case of the causal system. So in that case, what happens is that we can represent h of z equals to 1 into n is equal to 0 here, 1, 2, 3, 4, 1 into z to the power minus 0 plus 2 into z to the power minus 1 plus 0 into z to the power minus 2 plus 1 into z to the power minus 3 plus 2 into z to the power minus 4. Okay, so if we are given a series of number, it becomes quite easy to find out the z transform. Okay, it becomes quite easy to find out the z transform. Now say for example, if our origin would have been here, then this would have been 0, this is minus 1, and then this would be minus 2, and this should have been 1 and 2. So what we would have got, h of z equals to 1 into plus 0 plus 1 into z to the power minus 1 plus, okay. Now for a causal system, all these values, all these z values, they should be having a power of negative, not positive. Because if you see over here, these were the terms where the z, the power of the z terms were positive. Okay, that means they were associated with the non-causal part. Okay, they were associated with the non-causal part. Causal means from time instant 0 towards infinity. Okay, so previous to that, it becomes non-causal. So when we have this bilateral z transform, this bilateral z transform is basically considering the time points from minus infinity to infinity. Okay, for causal system, this n, it starts with 0. Okay, so in the next slide we get this equation, which is the generalized equation. So n equals to 0 to infinity x of n z to the power minus n. So this is called unilateral z transform. Similar is the case for the Laplace transform also. Over there, if the integral starts from 0 to infinity, then it is called unilateral Laplace transform. And if it is integral is minus infinity to plus infinity, then it is called bilateral Laplace transform. Okay, but for the causality purpose, we know that biomedical signals and systems, they are causal signals and systems. So we will mostly be dealing with the unilateral Laplace transform and this z transform. Okay, now what is the relationship between the z transform and the Laplace transform? Okay, so if you see, this is xt and this cap means we are sampling the xt. Okay, so it is nothing of x of nt multiplied by delta t minus nt. So what is this? Do you remember? This is basically the impulse train. Okay, this is basically the impulse train. So we are having x cap t equals to summation of n equals to minus infinity to infinity x of nt delta t minus nt. Now if we take Laplace transform on both the sides, we get x cap as summation of n equals to minus infinity to infinity. You may say, sir, why we have parted away with integral? Because when we have multiplied it with the impulse train, we have discretized the system. So we will be having some specific values. That's why we have changed the integral to the summation. But in the normal Laplace transform, you will be seeing that you are having the integral. Okay, so this is the reason why we have added up this. We have replaced integral with the summation. Okay, and this is because of this cap. Cap means sampled signal. Okay, so minus infinity to infinity x of nt e to the power minus nst. Okay, and z transform, it is this one. Now if you compare these two equations, can you see they both appear similar? Okay, and if we put z equals to e to the power st, then both the equations they become same. Okay, both the equation, the right hand side part of the equation, they become the same. So in that case, because we are trying to develop digital systems from where we want to develop, because digital systems they came much after than the analog systems. So the inspiration of the digital system design, it came from the analog systems. So we are taking all the principles and the learnings of the analog system, and we are trying to implement it into the digital system. You're getting my point? So we want that this right hand side options, they should be equal, and hence when they are equal when z is equal to e to the power st. So what is this as? S is equal to sigma plus j omega. So that becomes, this equation becomes z equals to e to the power sigma plus j omega t. So if you break it down, what we get? E to the power sigma t multiplied by e to the power j omega t. Modulus of z, e to the power sigma t. What is that? Right? But we are talking about this modulus. So इसका modulus क्या है? हाँ? Under root of cos square sigma t plus sin square sigma t. Cos square plus sin square, cos square theta plus sin square theta क्या है? 1 है. So it is equal to 1. Okay. So 1 means it is basically a unit circle having cos omega t, cos sigma t plus j sin j. This modulus, it is basically a circle. It is giving you an information about the circle. Okay, and what is the phase? Phase is j omega. Sorry, omega t. J is the complex, so it is the omega t. Okay. Now, when sigma equals to 0, this thing, and yeah, this one is, oh sorry, uh, yeah. So yeah, modulus of a, when sigma becomes 0, because we are talking about this, we are talking about this j omega, na? Sigma plus j omega. So when we get into the frequency axis, when sigma is 0, so when this is 0, then we get modulus of z equals to 1. Okay? And at the same time, we have z equals to e to the power j omega. So cos omega t plus j sin omega t. So it is nothing but the equation of a unit circle. So this is the explain So we are having sigma, and then this is the j omega left. So when sigma is less than 0, so what will happen? Our value will be less than 1 e to the power sigma t. It would be e to the power minus sigma t. So it will be less than 1. So this left hand plane, it comes over here. Similarly, if sigma is greater than 0, so this right hand side plane, it becomes, or it maps outside this z plane. And when we have sigma equals to 0, this j omega axis, it maps onto this unit circle, because modulus of z, it becomes 1. Okay, it becomes 1. So what does this signify? So this whole frequency component, which is from minus infinity to plus infinity, it has mapped into 0 to 2 pi. Okay, so after that, what will happen? After that, the other frequency components, they will again be moving on to this unit circle itself. Okay, now when that happens, it becomes a many to one mapping. It becomes many to one mapping. Okay, so when it becomes many to one mapping, so that means one frequency in the analog domain, they will be mapped into multiple digital frequencies. Okay, both in the positive domain and the negative domain also. Okay, so what happens is that when we talk about any signal, we are having two frequency components. One is the sampling frequency, and we have discussed that sampling frequency in the digital signals, it is the highest frequency. So where is the highest frequency over here? Highest frequency is at 2 pi. So the sampling frequency, it is directly placed at this position. Then what is the next frequency? The next frequency is our signal frequency, and we have discussed that there is a Nyquist theorem wherein we said that the sampling frequency should be greater than equal to 2 of fm. So under the restrictive condition, what will happen? Fs should be equal to 2 of fm. So fm should be equals to fs by 2. So it should be placed at pi. So at pi we will be having f of m. That is the maximum frequency within of the signal. Okay. So because of this, so what will happen over here, if you want to look into the frequency component 0 to 2 pi, and this is the amplitude. So what will happen? We'll be having 0 to pi, which is f of m. Okay, and again we said that when we are what do you call this sampling the signal, what we are doing, we are basically mirroring the frequency component. So the mirroring of the frequency component would be done. So 0 to fm, again 0 to fm would be there. Okay, so 0 to pi, whatever the frequency component is there, it will be again mapped in the range of pi to 2 pi. Okay, but what happens if our fm, it is greater than fs by 2? So in that case, our fm will be in this form or somewhere over here, but there should be a mirroring effect. So due to that mirroring effect, what is happening? So this is say pi plus delta f, say for example, here we will be having pi minus delta f or delta omega, because in radians if you talk about, so it will be omega. Okay, so pi minus here. So what is happening? So fm, this area or omega m, this was the high frequency components, and herein when it is repeating for the mirroring one, this is the low frequency component. So the high frequency component and the low frequency component, they are mixing, and when they are mixing, this phenomena it is called aliasing. Okay. So what we should do? We should band limit the signal before we are digitizing the signal, which we have already discussed. Now, usually what happens is that we do not band limit the signal such that the maximum frequency falls at pi. We keep it slightly lower. So what it does is that it allows us to have a dead band. This is called a dead band. So somewhere over here we will be having the FM, and somewhere over here when it is when you are talking about this, so there will be a region where there will be no frequency components, and from there the DC frequency will this FM will start pi. So suppose this is delta f or omega, delta omega, so pi minus delta omega, and over here we will be having pi plus delta omega. Okay, here we will be having pi minus delta omega. So this 2 of delta omega region, it is called the dead band. Okay, it is regarded as the dead band. So what it does, it eliminates the chances of aliasing altogether. Why? Because if you see, under the critical condition fm equals to fs by 2, so where do you implement, or where do you band limit the signal? We band limit the signal in the analog domain, right? By using analog filters, we band limit the signal. And we already discussed that we cannot have, or we cannot design analog filters using the calculated resistance and other passive component values. So there will be some deviations. If some deviation happens over there, and due to some reason your cutoff maximum frequency, it crosses this pi frequency thing, whatever should have been the legal frequency. If it passes that legal frequency, theoretical legal frequency, then you will be introducing aliasing effect. Okay, you will be introducing the aliasing effect, and because of that reason, what happens, we want to band limit, we do not want to work at this critical limit, and we usually have this fm um, which is slightly lesser than this fs byte. Okay, slightly lesser than this fs byte. So this is the aliasing. So relationship between ft and z transform. Okay, so if you see, z equals to r into e to the power j omega. Okay, so if we perform this z transform, from here we can say xz equals to summation of n equals to minus infinity to n, infinity x of n z to the power minus n, which is the z transform equation. Now if we place this value over here, r into e to the power j omega, similarly over here xn into r into e to the power j omega. So if you look, summation n equals minus infinity to infinity xn of n r to the power minus n e to the power minus j omega n. So what we get is that this is nothing but the Fourier transform of this thing, uh, of the signal x of n. Okay. So if r is equal to 1, x of e to the power j omega, it is equal to the Fourier transform of x of n. Okay. So we already discussed what is Z transform and how does it relate to the Laplace transform. So what is the region of convergence for the Z transform? Because if you see, we are dealing with circles over here. Okay. So wherever you place the pole, so where is the right hand side applied? Right hand side is applied. Outside, whatever is the location. So if I have a pole over here, so and another important thing, this y-axis, it is being converted into a circle, right? So the region of convergence will also be a circle like this. Okay. And since the region of convergence in Laplace transform for causal signals and system, it was on the right hand side. So in this case, where it is placed, it is outward. Okay. From the same analogy from the Laplace transform. Okay, it would be outward. Okay. So if I have, and does it engulf the frequency axis? Yes, it engulfs the frequency axis in this case. So the system will be stable and causal. Now if I move this pole outside, so we'll be having a new circle like this, and we'll be having the region of convergence outside, and this frequency axis, it is not included, and hence that means the system will not be stable. Okay. So we cannot place the poles outside the unit circle. All the poles should be placed into the unit circle. Similarly, like to the Laplace domain, where we can place the zeros, zeros can be placed anywhere. So in the z plane also, the zeros can be placed anywhere in the z plane. You please go through this. You should be able to understand. I have already discussed all this. What is system stability and how is it determined? Using poles and zeros for both continuous time and discrete time. So everything I have discussed already. So aliasing I have already discussed. Then there is a term called spectral leakage. So in the spectral leakage, what happens? So the definition of the spectral leakage is it occurs in the spectral analysis, particularly when the discrete Fourier transform is performed, and refers to the spreading of the signal's energy across a range of frequency bands in the computed spectrum. Okay. So what is happening over here, spectral leakage? If you see, if we are having a frequency component like this, so if you look into the frequency response, it should be quite sharp. Okay. But when we are applying any window, or we are no, window means we talked that for DFT we have to truncate the signal. Okay. Truncate means we are applying a window and we are taking the signal from a specific part of the time. Okay. So in other time instances it becomes zero. Now due to this reason, what is happening, if you see, the bandwidth of the signal of this signal, if you look into the window response, it has become wider, and apart from that you are having some side lobes also. So what is happening, in ideal case, beyond these frequency points there would not have been any signal component, frequency components, but because of the unusual truncation of the signal, what has happened, the frequency components, they are spilling over across the frequency axis, and this spilling over of the frequency component, it is regarded as the spectral leakage. Okay. So if you have a rectangular window, you can see the rectangular spectrum, it will be something like this. So you see, if you are having, or we'll be having something like this. Okay. The side lobes, and these side lobes, they will be interfering. if you are having hand window in the time domain, the hand spectrum, if you see, it becomes limited after some time. Then if you are having Gaussian window in the time domain, again if you see in the Gaussian spectrum, we are having some side lobes, but they are getting truncated. And another important thing is that if you look over here, the bandwidth is higher as compared to the Gaussian spectrum. So comparing these three things, so we get the information that if we use the Gaussian window function for the truncation, it will help us in minimizing the spectral leakage. We cannot stop it, but it will help us in minimizing the spectral leakage. Okay. So how does zero padding help in spectral analysis and what are its limitation? We already discussed zero padding. What it does, it increases the visualization of the uh, visualization resolution of the frequency axis. It does not improve the frequency component, but it improves the frequency resolution just for visualizing purpose. Okay, and clarity in the spectral leakage visualization. Zero pointing can make the continuous nature of the window signals Fourier transform more apparent in the discrete output as it effectively samples the DTFT at more points. So it is just giving you a visual representation. Okay, limitations. It is not adding any new information. It does not reduce the spectral leakage. Spectral leakage can only be reduced using by using yeah, time domain window functions which are slowly tapering. If you see in the hand window, the tapering rate it is quite fast over here, but in the case of Gaussian window, it is very slow. So we have to use a window function wherein the tapering is happening at a lower rate. If you are having a window whose tapering is happening at a higher rate, then it will increase the spectral leakage. Okay. So, and another important thing, if we increase the zero padding, it will increase the computational cost. Okay. So these are some of the key differences between the aliasing and the spectral leakage. So